Hi guys, we want to start Unit 2, and Unit 2 is really on different types of bonds. We're going to look at molecular and ionic compounds, their structure as well as their chemical properties. So just remind you that with ionic bonding, we're talking about a transfer of electrons. And so the metals are going to transfer electrons to the nonmetals, and then the two are going to form bonds because of electrostatic attractions. You can also say that cations, which are positively charged, and anions, which are negatively charged, form electrostatic bonds based on opposite charges. There's a note that cations and anions may be polyatomic. Generally, we see more anions. The one cation that we'll encounter frequently is the ammonium cation. Covalent bonds, the big thing to remember about covalent bonds, nonmetals, okay? One nonmetal atom shares one or more pair of electrons with another nonmetal. So our electrons are transferred in ionic, but they are not transferred in covalent. Basically, the electron density from the valence electrons of both atoms is going to increase between the two nuclei. And so covalent bonding, again, between nonmetals. So molecules, and the term molecule, and if you see that in an FRQ, if it defines something as a molecule, that's going to be covalently bond. That's going to be two or more nonmetals bonded together covalently. And the bonds can be nonpolar covalent or polar covalent, and we'll talk about ways to tell those apart. We have encountered electronegativity before, especially when we talked about periodic trends. If you'll remember, electronegativity increases as you go across a period and decreases as you go down the periodic table. And electronegativity, there needs to be a T there. So it's an element's ability to attract bonding electrons. So when moving from left to right across a period, more protons are added to the nucleus. The valence electrons are in the same shell. As the positive charge increases, it exhibits a greater force of attraction on those electrons, according to our friend Coulomb's law. So that's going to pull the electrons closer to the nucleus. It's going to decrease the radius. So when two atoms are involved in a chemical bond, the bonding electrons experience a greater attraction for the positive nucleus that is closest to them in accordance to Coulomb's law. When moving up and down a group, so when moving up a group, each element has one less shell and therefore a smaller radius. When moving from left to right across a period, more protons are added to the nucleus and the valence electrons are in the same shell. As the positive charge increases, a greater force of attraction is exerted on the electrons in accordance with Coulomb's law. That's going to pull the electrons closer to the nucleus and decrease the radius. Looking at electronegativity and bond polarity, the greater the electronegativity value, the more strongly the element is going to attract electrons to itself. And so basically we get our electronegativity difference by subtracting the electronegativity values of the two atoms that are bonded together. And it's generally thought of that if the difference is 0, then the bond is completely covalent. Most chemists still consider a bond to be covalent when the electronegativity difference is 0.5 or less. So that's the generally accepted range of being nonpolar covalent. Completely covalent means that the electrons spend an equal amount of time around each atom. That's only true if the two atoms have the same electronegativity. So be careful of that. Sometimes you'll be asked to compare the bonds or the polarity of an oxygen molecule and carbon dioxide, let's say. And so remember, if the two atoms have the same electronegativity, they will be completely covalent because if you look at oxygen, if you have O2, each oxygen has an electronegativity of 3.5. But if you look at the difference, 3.5 minus 3.5 is a 0. So polar covalent means that the electrons are actually going to spend more time around the electronegative atom. So a polar bond will have a net positive end and a net negative end. A bond is considered to be completely ionic when the electronegativity value is 3.5. Electrons are not shared in an ionic bond. Sometimes ionic compounds, like if you look at aluminum sulfide, it actually has polar covalent bonds because the electronegativity difference between the aluminum and the sulfur is 1.0. So all polar covalent bonds have some ionic characteristics. So basically, if you look at types of bonds, these balloons are going to represent the electron density distribution. You notice our fluorine molecule is perfectly covalent. The electrons are evenly distributed around the two fluorine atoms. And that should make sense because our electronegativity difference is 0. But in the HF molecule, this blue region represents low electron density, and we use this little delta symbol here. So since it's low electron density, it's slightly positively charged, and the green region represents high electron density. More electron density in that area is going to make that end more slightly negative. So the electrons are going to spend most of their time around the more electronegative fluorine atom. The electronegativity difference in this molecule is 1.9. And if you go back to that chart, 1.9, you notice is really almost ionic. So the fluorine atom is going to develop a partially negative charge, and the hydrogen atom end is going to develop a partially positive charge. Now, in our sodium fluoride, the electron that donated to fluorine spends all of its time around the fluorine atom. And so the electronegativity difference, if it was perfectly ionic, that is exactly what would happen. And it turns out that the electronegativity difference between sodium and fluorine is a 3.1. If we go back, perfectly ionic's 3.5. So that electron is spending most of its time around the fluorine molecule. Polar covalent bonds, so things to note, the atom with the higher electronegativity is going to develop a partially negative charge, and the atom with the lower electronegativity is going to develop a partial positive charge. And that charge will be equal in magnitude but opposite in charge to the more electronegative atom. So the sum of the partial charges in any molecule or ion is always equal to the overall charge of the species. So let's talk about how we're going to determine our bond type. So the bond between any two like atoms in a compound must be covalent. I don't think I have that one in there. I don't have the hydrogen-hydrogen one in there. But if I add hydrogen and hydrogen, that bond must be covalent because the electronegativity difference is 0. Here, this bond, our electronegativity is 0.4. The bond is actually somewhat polar because there does exist an electronegativity difference. However, something usually less than a difference of 0.5 is considered to be nonpolar. So we're going to say that this is a nonpolar molecule. If we look at hydrogen and bromine, though, this is going to be an electronegativity of 0.7, and this is thought to be a polar covalent bond. Polar covalent bonds usually have an electronegativity difference between 0.5 and 1.9. So the bond is polar. The partial positive charge will be our lower electronegativity, so the hydrogen end of this will be partially positive, and bromines are more electronegative element. And so, whoops, I didn't write that correctly. That will be partially negative. So the partial negative charge is on the bromine atom. Now, these partial charges are a lot smaller than they are in something that has a bigger electronegativity difference. But again, we still have a partial positive and a partial negative charge. Looking at, this is a CO2 molecule. And when we look and define the molecule, we look at individual bonds. We do not look at the entire molecule here. When we look at shape, we'll talk a little bit more about that. And so we're basically, the bond between one carbon and one oxygen has an electronegativity difference of 1. And so each bond is considered to be a polar covalent bond. Lithium fluoride, notice our electronegativity difference here is at 3.0, and so ionic bonds have an electronegativity difference between 2 to 3.5, and since 3 definitely falls in that range, this is an ionic bond. The electron spends pretty much all of its time around that fluorine molecule. Now, electronegativity difference is not the only factor that determines if the bond is covalent or ionic. Generally, bonds between a metal and a nonmetal are ionic, and bonds between two metals are covalent. And so looking at the chemical properties of the compound, that's going to be the best way for us to characterize the bond type. So properties of ionic solids, and you guys are going to get some data from a chemical bonding lab, and so you want to remember some of these properties to be able to differentiate compounds from each other. So ionic takes a lot of energy to break apart ionic crystal lattices, so you must add a lot of heat to get them to melt. And because of that, ionic solids have very high melting points. They're considered to have low volatility. They don't break apart readily because it takes an incredible amount of energy to break the ionic bonds and let this solid enter the gas phase. And so our ionic solids, we're going to see they're very hard and they have very high melting points. If we hit them with a hammer, they are considered to break apart into surfaces that have definite angles to one another because these little ions are lined up in repetitive patterns. And so this brittleness, it tends to result from the repulsion of like charges as one layer slides over another. So ionic compounds are not malleable. And they are not ductile. So we can't really hammer them into sheets or anything like that because they're likely to just fragment. And so if you try to crush them, they'll break apart along particular planes. So a simple test for determining if water contains ions is to run electricity through it. Most ionic compounds are soluble in polar solvents. They conduct electricity only when they are molten, which is melted, or dissolved in a polar molecule. And the higher the concentration of ions in the solution, the higher the electrical conductivity. So you will electrocute yourself if you drop your hairdryer in the bathtub while you're in it, because there are ions in the tap water. Now, you could try this out, but I don't recommend it at home. Distilled water has a very limited ability to carry electricity. So if you had a tub filled with distilled water and dropped a hairdryer in it, it is not likely that it will conduct electricity. Ionic compounds are not going to dissolve in nonpolar solvents. Some properties of covalent compounds. Most covalent compounds have much lower melting and boiling points than ionic compounds. They are usually soft and flexible. And a biggie is that most covalent compounds do not conduct electricity when dissolved in water. Now, acids are going to be an exception to this rule, but a common chemistry question is that you have a mixture of salt, or you have two substances, you have salt and you have sugar, and you don't know if what you're ready to add to your recipe is salt or if it's sugar. Both of these compounds are going to dissolve in water. So it's not like one is soluble and one is insoluble. But when dissolved in water, one of these substances will conduct electricity and the other will not. So your salt's going to conduct electricity, but your sugar will not. So that's a very good differentiation of whether your substance is salt or whether it is sugar. All right, our polyatomic ions that you all remember and love so well is actually a combination of nonmetals or metals and then nonmetals. They are bonded together to form a polyatomic ion. So the polyatomic ion that acts as an ion, that entire molecule, though, is often held together by covalent bonds. But the bonds between the atoms are generally nonpolar covalent or polar covalent. Crystalline solids, ionic solids are going to cleave along planes because the ions in the solid are arranged in a structure that repeats itself in all three dimensions. So ionic compounds do not exist as individual units containing a cation and an anion. Sodium chloride does not exist as one sodium cation bonded to one chlorine ion. Instead, the ions are arranged in an orderly fashion. They're called unit cells, and that is why then those charges are just keeping that entire structure together, and that's why when we hit them or try and crush them, well, they'll cleave along the plane. And the ions are going to be arranged in a way that's going to maximize the Coulombic forces of attraction between the cations and the anions, and it minimizes repulsive ions. So the way in which ions arrange themselves is actually going to depend on the size of the cations and the anions, and then the ratio of cations to anions. Looking at sodium chloride, each sodium cation is surrounded by 6 chlorine anions, and each chlorine anion is surrounded by 6 sodium cations. So if you kind of look at this, it looks to me Which of these are sodium? So we have a sodium ion and we have a chloride ion. Which of those is bigger, a sodium ion or a chloride ion? Hopefully you've told me that the sodium ion is bigger. So if you were asked to identify in a particle diagram, the green ones are going to be the sodium ions because they are bigger. The gray ones, or blue, gray-blue ones, are going to be the chloride ion because they are smaller. And again, we want to maximize the forces of attraction in this arrangement and minimize the repulsive forces. So this is a unit cell. This lattice contains 8 cubic cells. These cubes are exactly the same. Basically, in reality, the particles are touching each other. There aren't any red and black lines in reality. But this simple unit cell kind of shows you what things look like. This gives you some possible arrangements. You do not need to memorize the structure. These images are basically here to help you visualize the possible arrangement of ions in ionic compounds. So I'm just going to kind of flip through these guys, okay, just some possible arrangements of ions. Let's go to metallic solids. So our ionic ones, you'll remember, had very high melting points. Our covalent solids did not. In between, we're taking a little bit look at metallic solids. In metallic solids, the bonding is not covalent. There are not enough electrons, so the bonding is going to result from the attraction between nuclei and what are called delocalized valence electrons. And metallic solids are usually your transition metals. So the bond strength is going to increase as the number of bonding electrons increases. So this is kind of a nice little example here. Sodium has 1 electron beyond the noble gas configuration, so its melting point is a lot lower than iron, which has 8 electrons beyond the noble gas configuration, and so iron is going to melt at a much higher temperature. So metallic bonding, this is called an electron C model. So the electron C model accounts basically for the properties of metals. Notice electrons can move very freely. So the free movement of electrons allows metals to conduct electricity, and it also enables metals to conduct heat rapidly. If you heat one end of a metal bar, you'll transfer heat to the electrons in that area, and those energized electrons will move to the other end of the bar, carrying the heat with them. And you'll notice there are no directional bonds, so metals tend to bend, not break, when you hit them with the hammer. And so this is going to be a way that we can differentiate a chemical that exhibits metallic bonding from one that exhibits ionic bonding. Both the ionic bonds and the covalent, or the ionic bonds and the metallic bonds will conduct electricity. Our metallic bonding can actually conduct electricity as a solid, and they are malleable and ductile, whereas if we hit our ionic compounds, they will cleave along those planes. So metallic bonds are very strong. Metallic bonding has low volatility. So some terminology we have a solution. That's going to be a homogeneous mixture of 2 or more substances. Solvent is the thing doing the dissolving, where the solute is the substance that is being dissolved. So I like that. So this is doing the dissolving. Commonly, it is water. and the solute is what is being dissolved in it. An alloy is going to be a solid solution. It is two or more metals. It's a mixture, really. One or more nonmetals, but usually one or more metals. Our solution will never separate as long as the pressure and the temperature remain constant. When we look at alloys, there are two types of alloys. There are interstitial alloys, and these, steel is actually a great example. Steel is a mixture of carbon and iron. And so atoms with a small radius are going to occupy spaces. So interstitial means between spaces. Interstitial alloys. It is considered to be a solution. This is a homogeneous mixture, so this is an example of a solution. Iron is the solvent, and carbon is the solute. Some properties of steel. Pure iron lacks directional bonds. Pure iron's pretty soft and ductile. Carbon forms strong directional bonds with the iron atoms. And what that's going to do, if you look back at this picture, so by itself, the pure iron is kind of malleable. Steel is going to be more rigid. The carbon helps stabilize the structure of it, and so this is going to make steel much stronger than iron. By filling the interstitial spaces and forming bonds with the neighboring iron atoms, this alloy becomes a lot less malleable. Generally, the more carbon you add, the stronger the steel becomes. And so a steel hammer basically needs to be stronger than steel nails so that the nails don't bend or dent the hammer. Therefore, hammers are going to have more interstitial carbon than nails. Now, interestingly enough, if you add too much carbon, the steel actually becomes brittle. That's going to be different, and you can see it right away in the diagram from what are called substitutional alloys. In substitutional alloys, the radii of the solute and the solvent atoms are actually similar. So brass is a good example of a substitutional alloy. So in a substitutional alloy, zinc is going to be substituted for some of the copper atoms. So our zinc in this case is the solute, and the copper is considered to be the solvent. And to be a substitutional alloy, the metals have to have a similar atomic radii. So mixing the metals can produce different kinds of properties. This is important when they're like making bicycles and things like that. And alloys are normally going to be able to conduct electricity. So that ends our first discussion of types of chemical bonds. And so you do have some homework problems assigned. And so I want you to kind of get started on that. But again, always email me if you have any questions. Thanks, guys.